All right, let me try another one here. This is chapter 38, number, what was it, 62. And 62 talks about this diffraction gradient, so I'll kind of represent something with a lot of slits in it and a screen. And it says here too closely spaced wavelength. And so if we have wavelength 1 and wavelength 2 and they come in, they're going to spread out. And we know that there'll be a bright spot at m equals to 0. That is, of course, the sine theta equals to 0. And that would be true for any wavelengths. But as we move up the screen or down the screen, and we get to m equal 1, m equal to 1, the shorter wavelength will show up at a slightly different angle than the longer wavelength. And so there'll be an angular separation between those two. And this question is really going down those lines. It wants to know then what is the separation in angle for one wavelength, the angular separation. And of course, you would be interested in that for a number of reasons, but one of them would just be simply because, oh, hang on here, I need to adjust the camera. But one of them would be because the, you wanted to separate these off. If you're a scientist, you want to know, okay, what are these two different wavelengths? They're close together, and want to know how much they differ by, or even if there are two of them. And as an engineer, you might want to be communicating some kind of communication. This is multiplexed, and so one communication is going down with one wavelength and another one, and then you've got the two in the same cable or in the same fiber optics, and then you got to separate them out so that you can send channel 1 to, communicating with this person and channel 2 communicating with the other one. So you've got them, communications multiplex, but eventually you've got to separate them to see them. And so this is a good example of that, of how you might go about doing that. Of course, there would be the same thing at m equal to 2. And I point that one out because I think that's where they later on they say here is, yeah, in the second order. And so part B is asking in the second order. But this should be able to figure all this out from this relationship, which they say is our equation 38.7. And you can see that by taking the derivative. And so if I take the derivative with respect to the wavelength, I get the d, and the derivative of sine is cosine theta, and then the chain rule is d theta d lambda. And so that's the part I'm looking for, the angular spread per wavelength. And so how could I tell these or separate them? How far apart are they? On the other side of the equation, it's an easy derivative. It's just dm. And so now you can get the d theta d lambda, so the angular spread per wavelength as the order over the d and cosine theta. And so that's, I guess, part A right there. Where did this equation come from? And so diffraction gradients can be used for just that. You can separate out wavelengths, and their angular spread is connected to their wavelength spread, depending on what order you are and what angle are you at. And of course, that's why your higher orders work better. Not only is this number bigger, but then this angle is bigger and therefore smaller, and so you can separate things better at the second order or third order. Of course, then the intensity is also dimmer too, so that's not always workable option, but if you can detect these lower intensities, you get a bigger separation. So on to part B for this problem. Part B then says you have a square gradient which has 2 centimeters on each side and contains 8,000 equally spaced slits. Well, that right there is telling me what D is, because D is the distance between each slit. So I'm going to put 0.02 meters representing 8,000 different slits, or what we often say lines, in them. Or maybe I should just use their word, slits. Okay. So grabbing my calculator, 0.02 divided by 8 6,000 gives me 2.5 times 10 to the minus 6 meters per each slit. And so that's the distance between each of those. Now, it says we want to study mercury here. And it says two closely spaced lines are emitted, and they give us the two wavelengths. What is the angular separation? So let me rewrite this as d theta equals to md cosine theta over d lambda. Or let me change it from its calculus form and say, okay, the change in the wavelength between these two would be whatever order we're looking for, divided by d, divided by cosine of theta, and then the wavelength, the difference between those two. No, all right, so I know that we're at order 2, and I know d was the 2.5 times 10 to the minus 6 that I just calculated. The angle, though, is worth pausing for a moment, so I'll just kind of leave that alone there. And then come over here and just say, well, this is the separation in the wavelength. And so they give one at 500, well, maybe I'll just put it over here, delta lambda. They give the longer one at 579.065 nanometers, and the shorter one at 576.959. So grabbing my calculator here, 579.065 divided by 576.959. That's a difference of only 2.106, and I'll put nanometers. And I guess I should put meters here. Now, I can't really put anything for an angle quite yet, but let's come back really to this equation. This can tell me the wavelength, because these are shooting up, and there's not much of a difference between them. So if I just write d sine theta equals to m lambda, and I use the d that we just got, the 2.54 times 10 to the minus 6th, and then I have sine theta. And if we're talking about order 2, then we can put in the wavelength, and technically each of these are at a slightly different angle, but they're nearly the same. So let me just kind of get maybe an average angle and an average wave, well, and I'll get that from the average wavelength here. So let me take this as the 579.065. I will add it to the 576.959 and divide that by 2. Remember, times 10 to the minus 9 meters here. And this is meters here. And so this will give me an idea of what angle that is. So 579.065 and 576.959, add them together, divide by 2. So there's kind of the average wavelength. Multiply that by 1 times 10 to the negative 9 to change it into nanometers, and then multiply that by 2. So that's this side of the equation. And then if I divide that by 2.5 times 10 to the negative 6, we're looking at about 0.462. And that's a good question if it is a small angle. It's getting to the point, usually we say a small angle is anything less than 30 degrees, which is about a half, a sine of 30 degrees, about a half. So I guess we're just there. Let me look what mode on my calculator in. I'm in degrees. So if I go inverse sine here, we're at about 27 0.5 degrees. So I won't take small angle. I'll just actually use my inverse operation and then come back over to here and then say, okay, I can put in that angle of, what I say, 27.5 degrees. And so the change in angle is, and so let me just, while I've got that angle in there, go cosine of that last one. So there's the cosine of the angle. And as long as I'm working with the denominator, so I've got cosine of the angle, okay. And I'll work with the denominator, so let me take that and go 2.5 times 10 to the negative 6. So that's the denominator. Whoops. Denominator. I'll take the reciprocal of that and multiply it by the 2 up here, and multiply that by the 2.106 times 10 to the negative 9. Ooh. I don't like that at all. What did I do wrong here? Oh, I think I hit enter twice. Crap. Okay, well, let me try that again then. All right, so clear. All right, so across the top, let me go 2 times 2.106 times 10 to the negative 9. Then I'll divide that by 2.5 times 10 to the minus 6. And I'll divide that by cosine of 27.5. All right, and that gives me a 0.001, I'll just call it 899. I need to be a little careful with my units. Although I put this in degrees, you can see that I set this formula up as real numbers. So this is in radians. And so I guess if I want to finish it in terms of degrees, I need to go times 180 degrees for each pi radians. And so they would be separated by 0.109 degrees. So about 1/10 of a degree. So again, they're going to be really close together. Going to be hard to tell. But depending on your equipment, far enough to separate out for either your communications and your engineering or for your scientific measurement. All right.